our hierarchy today, later on be given by Professor Anpo for Shiroya and Yamashita.
Thank you, Mr. Chairman. Today, I'd like to talk about the interaction of NO and CO with kappa plus GSM5 catalyst and their reaction. Ion exchange kappa GSM5 catalysts have attracted a great deal of attention as a potential catalyst for the direct decomposition of NOx into nitrogen and oxygen. We have recently reported that in the presence of MO, UV irradiation of well-degassed kappa zeolites such as white zeolites and morganite and GSM5 and kappa on silica catalysts lead to the catalytic decomposition of MO into nitrogen and oxygen even at 275 Kelvin. These results suggest that partially reduced kappa species play a significant role in the catalytic and post-catalytic decomposition of NO. In the present work, therefore, the characteristics of kappa species in kappa GSM5 and their interaction with NO and CO molecule are investigated by means of in situ photoluminescence, ESR, and IR measurements. A kappa 2 GSM5 sample were prepared by ion exchange method. The loading of kappa is about 0.1 to 2.3 weight percent. Prior to the spectral measurement and reaction, the sample was degassed at 607 Kelvin, heated at the same temperature in the oxygen, and then finally evacuated at the desired temperature. The condition for the measurement of photoluminescence, ESR, FTIR, and reaction conditions are shown here. The preparation of kappa plus GSM5 catalysts were prepared by the evacuation of kappa 2 plus sample at high temperature. As you know, the kappa 2 plus exhibit a typical ESR spectrum due to kappa 2 ions anchored in zeolite framework. The increased evacuation temperature of the sample led to the drastic decrease in the intensity of ESR signal, with minor changes in their spectral parameters and line shapes. And these results suggest that chemical reduction of kappa 2 to kappa 1 has occurred in this treatment. In fact, the color of sample changes from blue light to white. Only these catalysts in which a very weak ESR signal assigned to kappa 2 could be observed exhibit a characteristic photoluminescence. This figure shows a typical photoluminescence spectrum and its corresponding excitation spectrum of kappa plus GSM5 catalysts, which were prepared by the evacuation of the kappa 2 GSM5 samples at 1173 Kelvin. According to Professor Krieger, the chairman, and Professor Zink, this absorption band is attributed to the electron transfer from 3D10 to 3D9 for S1. And this photoluminescence is attributed to a radiative decay processes from the excited state of kappa plus to ground state of kappa, 3D10. This figure shows the effect of the addition of NO on the yield of photoluminescence spectrum of kappa plus GSM5 catalyst that has been prepared by the evacuation of the kappa 2 GSM5 samples at 1073 kelvin. As shown in this figure, the addition of NO onto the just formed kappa plus GSM5 catalyst leads to the efficient quenching of the photoluminescence, not only in the yield of photoluminescence but also lifetime it becomes shortened, quenched. And this extent of this quenching depends on the pressure of added NO. This figure shows the ESR spectrum observed by the addition of low pressure of NO onto the kappa plus GSM5 catalyst. Although I skipped the detailed explanation of this signal, anyway, this signal is assigned to the NO absorbed on the kappa plus ion, and this signal is represented by kappa plus NO adapted species. And another, this species signal is attributed to the remaining unreduced kappa 2. But this signal is attributed to the NO absorbed on the kappa plus. And this nitric NO adapted species is stable in the presence of low pressure of NO. However, under UV radiation, this signal decreased, and after stopping the UV radiation, this ESR signal gradually increased and recovered to the original intensity. This figure shows IR spectrum of NO absorbed species on kappa plus GSM5 catalyst at 298 Kelvin. As shown in this figure, the main band at 1811 Kaiser is assigned to the mononitrogen adapted species. It is written like this, kappa plus NO. Another minor band can be identified as NO species absorbed on the unreduced remaining kappa 2 plus anions. And this species also stable in the presence of low pressure of NO. However, under UV radiation, this peak decreased with increasing the time of UV radiation. And after stopping of UV radiation, this signal again gradually increased and recovered to the initial intensity level. These results suggest that this nitric adsorbed species is stable in the presence of nitric NO molecule. However, under UV radiation, some reaction occurs. In fact, UV irradiation of kappa plus GSM catalyst at 270 Kelvin in the presence of NO lead to the formation of nitrogen oxygen. This figure shows the reaction time profile of the catalytic decomposition of NO. Under UV radiation, NO decomposes into nitrogen and oxygen, having a good linearity with UV radiation time. This result clearly suggests that decomposition of NO proceeds catalytically under UV radiation on the kappa plus GSM5 catalyst, even at 275 Kelvin. This figure shows the effect of the evacuation temperature of the sample of kappa 2 GSM5 on the intensity of ESR signal due to kappa 2 plus and on the yield of photoluminescence spectrum due to kappa plus anions, and also on the yield of photocatalytic decomposition of NO at 270 Kelvin, and also on the amount of absorbed CO absorbed on this catalyst. As you know, the carbon monoxide selectively absorbed on the kappa plus species. So this result really suggests that with increasing the evacuation temperature of the kappa 2 DSM hydrogen leads to the reduction of kappa 2 to kappa 1. And at this temperature, number of carbon monoxide absorbed on the catalyst shows that about 95% of original kappa 2 ion are reduced to kappa 1 at this temperature. Anyway, this result shows that with increasing the evacuation temperature of the original kappa 2 DSM sample leads to the drastic decrease of ESR signal due to kappa 2 plus, and after then photoluminescence yield is increased with increasing the evacuation temperature. And also photocatalytic reduction, decomposition of NO also increased with increasing evacuation temperature. Such parallel changes indicate that the presence of kappa 1 species play a significant role in photocatalytic decomposition of NO on kappa 1 DSM-5 catalyst at 275 Kelvin. From these results, such reaction mechanism can be proposed for the photocatalytic decomposition of NO into nitrogen and oxygen at 270 Kelvin on the kappa DSM-5 catalyst. As I shown you, kappa 2 species are reduced by the evacuation at high temperature to a kappa 1. But this process is also occurred by the reduction of hydrogen at high temperature. But anyway, in this case, I only show the reduction of kappa 2 by evacuation at high temperature. And this kappa 1 is formed on the zeolite surface, and addition of NO leads to the formation of such nitrogen adductor species. In this species, kappa delta plus and NO delta minus. A small amount of electron transfer from kappa to NO. And after UV irradiation in this system, electron moved from D to 4S1. So excited state of kappa is 3D9 4S1. So this excited electron transfer into pi anti-bonding orbital of NO. This electron transfer results in the weakening of NO bond, so NO cleavage is occurred. And at the same time, electron transfer from pi bonding orbital of NO into vacant kappa site. And also this results in the weakening of NO bond. So on one kappa plus site, two NO molecule decompose. This could be the reason why under UV radiation NO decompose selectively into nitrogen and oxygen. Okay, now let me move to the next topic on the interaction of carbon monoxide on kappa plus DSM catalyst. This here shows the effect of the addition of carbon monoxide on the photoluminescence spectrum of kappa plus DSM-5 catalyst. This is original photoluminescence due to kappa 1 on the DSM-5 catalyst. And that time is about 85 microseconds, and corresponding absorption band is observed at around 300 nanometers, as I shown before. And addition of carbon monoxide leads to the shift of this photoluminescence band, and increasing the addition of carbon monoxide, this photoluminescence increased. As shown here, the addition of carbon monoxide leads to the efficient quenching of photoluminescence. because this photoluminescence is observed in the presence of carbon monoxide. But this spectrum is deconvoluted, this species and this species. So this species shows that original photoluminescence decreased, quenched, and this new photoluminescence is appeared. And this new photoluminescence increased with increasing the addition of carbon monoxide. According to Professor Clear, this new photoluminescence is attributed to the formation of the copper plus CO complex on the surface. This figure shows the effect of the pressure of added carbon monoxide on the IR spectrum due to carbon monoxide absorption species on the copper plus DSM-5 catalyst. This characteristic absorption band at 2156 hydrogen is attributed to the formation of copper plus CO complexes. This figure shows the effect of the amount of CO absorbed on the copper plus DSM-5 catalyst on the yield of photoluminescence due to the formation of copper plus CO complex and the intensity of the characteristic IR absorption band due to the Cu plus CO complexes. The IR absorption band due to the copper plus CO complex increased with increasing amount of absorbed CO and reached the highest intensity by the absorption of 2.8 10⁻⁴ mole of carbon monoxide and then become constant. On the other hand, new photoluminescence band at around 440 nanometer due to the formation of the copper plus CO complexes increased with increasing amount of absorbed CO molecule. And the maximum intensity is achieved by the absorption of about 2.75 10⁻⁴ mole of carbon monoxide. This figure shows the changes in IR absorption peaks at 2156 hydras due to the copper plus CO complex, and also this 2108 hydra is attributed to the Cu plus 13 carbon complex with increasing amount of carbon 13 CO absorbed on the copper plus DSM-5 catalyst, with increasing amount of carbon 13 CO due to the decrease of this peaks and increase of this peak due to copper plus 13 carbon monoxide. This result clearly shows that some exchange reaction is occurred on the surface. This figure shows effect of the amount of 13 carbon monoxide absorbed on the intensity of IR peaks at 2156 hydra due to copper plus 12 carbon monoxide, and also at 2108 hydra due to copper plus carbon 13 peaks, and also the total intensity of IR band due to carbon monoxide absorbed on catalyst. With increasing the amount of 13 carbon monoxide, this peaks is decreased and copper plus 13 carbon monoxide increased. But in this case, the total intensity of carbon monoxide is scarcely changed. So this result clearly suggests that exchange reaction of 12 carbon and 13 carbon monoxide is occurred on the surface via the formation of Cu plus CO complex. And this complex is quite stable even after the evacuation at 307 Kelvin. Some part of complex remain on the surface. But in the case of adsorption species of NO, nitrous adapted species is very weak interaction with carbon monoxide. So for catalytic reduction, decomposition of NO is inhibited by addition of carbon monoxide. Okay, now let me conclude my presentation. First, in situ photoluminescence, ESR and IR measurement of the kappa plus DSM catalyst in the presence of NO or CO allows the description of interaction of this molecule with kappa plus DSM catalyst at the molecular level. Second, evacuation of the kappa 2 DSM samples at high temperature leads to the chemical reduction of kappa 2 to kappa 1. Only the reduced kappa plus DSM catalyst exhibited a photoluminescence spectrum at around 420 to 570 nanometers. 3. The addition of NO onto the kappa DSM catalyst produces a nitrous adapted species, C plus NO delta minus, with a weak interaction with kappa plus, and resulting in the dynamic quenching of the photoluminescence. This species decomposes into nitrogen and oxygen even at 275 Kelvin under UV irradiation. 4. The addition of carbon monoxide onto the kappa plus DSM catalyst produces a kappa plus CO complex with relatively strong interaction with carbon monoxide, and this complex was stable up to the evacuation of the system even at 373 Kelvin. 5. The quantitative relationship between the number of CO absorbed and CO plus species on the catalyst was established, and the role of the kappa plus CO complex is in the exchange reaction between 12 carbon monoxide and 13 carbon monoxide were clarified. Thank you very much for your attention.
May we open the discussion? I have a simple question. You suggested a mechanism of Ungol decomposition where Hutu extract the electron from 3T to 4S. And then Ungol interact with the kappa. The electron will respond to antibody of Ungol from 4S.
Yes.
From the point of view of optical symmetry, I think it's impossible. This should be antibody pi antibody of should be interact with 3T factor, not 4S, I think.
I'm not familiar with certain theoretical parts, but our result really shows that kappa 1 is play a significant role in this reaction. And this, as I mentioned, this absorption is electron transfer from 3D10 to 3D9 for base 1. But this, however, this processes could be involve some charge transfer on the surface.
The last line is that electron transfer into pi from the this electron means the OS of But I think this because the optics make it difficult.
Yes, I know that. My point is actually excited state is not actually like that. This excited state could be involved some child transfer processes on kappa on the lattice oxygen. But this point is not clear at this moment.
Thank you.
If you could put the same transparency back on my question relates to the first line there. Could you explain what the chemistry is when you do this reduction from copper 2+ to copper 1+? From where does the electron come? My suspicion is that the copper 2+ exists here not as a naked ion the way you draw it, but in fact copper 2+ with a hydroxyl associated.
Maybe this process is surface hydrogen group or oxygen is involved with the reduction process.
I have some problems always with the chemistry, balancing the chemical reactions when people draw these very simple transitions. So can you have a sort of clarification for what the chemistry is? That's right. I end up with an oxygen atom floating around in the systems.
I have to ask you the last question here before we go to coffee break.
I had a question. First of all, I have a comment. The charge transfer of first ion, we need to advance the physics experiment to show very clearly, even at room temperature, the cells that don't into the system, you can see the energy shift, upshift instantly, which really tells you that the electron transfer from the first ion to NO instantly. That explains the charge transfer. Actually, I had a question though. When you talk about UV effect, the photon effect, you show slight exposure to the catalyst at approximately 5 hours. You see about 2.5% conversion under luminescence. My question is, it is common in physical chemistry to explain that this kind of phenomenon, you really absorb UV photon, and instantly this UV photon, through so-called internal conversion process, will convert the photon energy to the thermal energy. So even your experiments conducted at room temperature, but you actually effectively heat up the catalyst. You probably didn't aware of that, but you actually heated the catalyst.
No. Somebody affected different way. In this way, we excited to 180 that's the absorption of this compound.
If you change to different energy, do you still see the effect, or you don't see any conversion at all?
Yes, without the